Yes, sir.
Yes,
Yes, sir.
sir.
Okay,
Yes,
okay.
yes, sir.
Now, last day we concluded that if you sample an analog sinusoid at a frequency that is greater than twice the frequency of the analog sinusoid, then only you will be able to get back the original analog sinusoid by mathematical interpolation unambiguously, uniquely. So let's just recapitulate what we have observed, but in a different way. So as I have noted as observation, suppose we have a sinusoid xt with frequency small f, and it is sampled at a rate fs. The time interval for sampling is tau, such that fs is greater than twice f. All right, and the sampling starts at t equal to 0. Let's consider that there is another group of sinusoids represented by yt and given by that expression, where m can take on any positive integer values. All right, any positive integer value m can take on. So each member of this group of sinusoids is also sampled at the same rate, fs greater than twice f. Then what will be the sampled version of xt and what will be the sampled version of yt? That is the question. X and tau will be obtained simply by replacing t with n tau. That is x and tau, the sampled version of xt. Y and tau will be obtained by replacing t with n tau in this expression. So that is the expression. If you break it up, twice pi nm plus twice pi f n tau. Remember that n into m is an integer, positive integer. All right. So y n tau comes out as a sine twice pi f n tau. That means same as x n tau. Y n tau and x n tau, these are same. So under the conditions that I have mentioned, what will happen? You cannot distinguish between the sampled versions of xt and yt. That means I have chosen yt such that yt equal to what is the frequency of yt? Any member of yt, it's f plus capital M fs. That means the frequencies of yt and the frequency of xt, they differ by integer multiples of the sampling frequency. That means you cannot distinguish between the sampled versions of sinusoids whose frequencies differ by integer multiples of the sampling frequency. That is the conclusion. Not only that, if you consider yet another group of sinusoids, all right, zt, which is represented as minus a sine twice pi mfs minus ft. Here m also can take on positive integer values. What will be the sampled version of szt if it is sampled at the same rate as before? Fs greater than twice f. Simply in this expression, I have replaced t with n tau. So that is the result. What will be? What will it settle down to? Zn tau equal to a sine twice pi fn tau. Same as yn tau, same as xn tau. Therefore, here also you cannot distinguish between the sampled version of an analog sinusoid with frequency f and analog sinusoids with frequency mfs minus f, where fs is the sampling frequency. All right. So here in this case, because you cannot distinguish between the sampled versions of x and tau and xt and yt, we say that this frequency, group of frequencies, f plus mfs, they have been folded back into the interval f greater than 0 less than fs by 2. That frequency, fs by 2, it is called the Nyquist frequency or folding frequency. Similarly, in this case, those frequencies mfs minus f, it is several frequencies mfs minus f. So those frequencies also are folded back into the same interval, f greater than 0 less than fs by 2. So this is the phenomenon of aliasing. It has resulted from undersampling. So you may write down. যেতে পারবে? কারেক্ট আছে done.
Yes, sir. Done.
Sir, I think in y of n tau, the first term inside the sign bracket will be 2 pi nm fs tau.
Oh, sorry. Yes, right. Sorry. Yeah, no, that's all right. Twice pi nm fs tau, but what is the product fs into tau? That is 1,
Okay, sir. Okay.
isn't it?
Thank you. Yes,
Fs
sir.
into tau is 1
Yes, sir.
because fs is 1 by tau.
Okay.
Do you understand?
Yes, sir.
That's why fs into tau was there, but it's 1. That is twice pi nm.
So then for YT, there will be aliasing since sampling frequency and the frequency of YT is greater.
Right. That's what I'm trying to point out. All these frequencies, MFS plus F, they will be aliased into the frequency small f. That is what is happening here. That is the thing I'm trying to point out here. Aliasing will take place in case of YT.
Okay.
So we say that F plus MFS, these frequencies, they are aliased into the frequency small f, or they are folded back into the interval small, into the interval 0 to fs by 2. Small f is the alias of all these frequencies. If you just tell the reverse thing, that f plus mfs is the alias of small f, it doesn't matter. So you can, I mean, so far as expressing is concerned, so far as language is concerned, both statements are correct. All these are aliases of one another. But if you try to reconstruct an analog sinusoid from the sampled version of yn tau, it will be the sinusoid xt. Now this frequency fs by 2, this is called folding frequency or Nyquist frequency. Nyquist is the name of a person. Done?
Yes, sir.
Now about ZT. Similar thing will happen here. It will be twice pi m fs n tau. Fs into tau is 1. So it will be twice pi nm. And because there is a negative sign here, therefore Zn tau will be a sine twice pi fn tau. Next is we want to examine what is happening in the frequency domain. So we will deal with the frequency spectra of the continuous time signal and the discrete time signal as well. Remember that now we have obtained the continuous time mathematical model for the discrete time signal in terms of train of impulses. We can easily apply Fourier transform on that signal, on that expression for x at t. So frequency spectra of discrete time signals. We will try to establish the relation between the frequency spectra of the continuous time signal and the frequency spectra of the discrete time signal, the sampled version. Again, we are considering that now the case is general case, not a sinusoid. Remember, I will cite sinusoid as a special case, but this is not the case here. A signal xt need not be a sinusoid, can be a sinusoid as well as aperiodic signals, etc. All types of signals. Xt is sampled at a rate fs equal to 1 by tau to obtain a discrete time signal x at t. Fourier transform of xt, you know what's the expression? You just write down, I'll proceed. I hope you remember the expression for the Fourier transform. That is the basic expression for the Fourier transform. This is for the continuous time signal that is sampled. Integration over minus infinity to plus infinity xt to the power minus j omega t. So this is an integral transform, e to the power minus j omega t. This is the kernel of the integral. Kernel, it is called kernel of the integral. All right. That is the Fourier transform of xt, and we represent it by capital X j omega. What will be the Fourier transform of x hat t? Have a look at the continuous time mathematical model that we have developed. What will be the expression? Now Fourier transform of x hat t. X hat j omega is the Fourier transform of x hat t. So in place of x hat t, I have written down the summation expression. The summation involving scaled impulses. This summation is same as the product of xt with a periodic train of unit impulses. This one is a periodic train of unit impulses. And when we multiply that with xt, we get summation over x n tau delta t minus n tau. That follows from the shifting property of impulse function. Shifting property. Now have a look at the periodic signal, the periodic train of unit impulses. It will have its Fourier series, isn't it? So what will be the Fourier coefficient? If you consider the exponential Fourier series of this periodic train of impulses, what will be the Fourier coefficient? What do you think?
Half.
1 by tau.
1 by tau. Very good. 1 by tau. It will be 1 by tau for all frequencies, all discrete frequencies. What are these discrete frequencies? Fs, twice Fs, thrice Fs, 4 Fs, 5 Fs in the positive direction, and minus Fs, minus 2 Fs, minus 3 Fs, minus 4 Fs in this way. Very good. So all possible frequency components, all possible harmonics, they are present with equal strength, I should say, equal magnitude. They are present with equal magnitude. So this is the periodic train of unit impulses. So it will have its Fourier series. If 1 by tau is the Fourier coefficient for 0 plus minus Fs plus minus 2 Fs plus minus 3 Fs, etc., what will be the Fourier series? 1 by tau into summation over small m, say, equal to minus infinity to plus infinity, then e to the power jm omega st. Once we get the Fourier series expression for delta tau t, what I am trying to do here, I will insert the Fourier series expression in this place. This summation will be replaced by the Fourier series expression of delta tau. Then we will have a very convenient form of expression for x hat j omega to deal with. This is the expression Fm bar. It is the Fourier coefficient, complex Fourier coefficient. The order of the harmonic is represented by small m. Sorry. Is it done? I have considered FM bar simply because in general, the complex Fourier series, the exponential Fourier series coefficient, in general, it will be a complex quantity. That's why I have just written FM bar. If you write FM, there is no problem. হয়েছে?
Yes, sir.
Yes, sir.
Yes, sir.
And this is FM bar. I have derived the expression. Starting from the basic expression for the exponential Fourier series coefficient, I have shown that FM bar is equal to 1 by tau for all m. From m equal to small m takes on integer values from minus infinity to plus infinity. So this is FM bar. It has a value of 1 by tau for all values of m. That means for all values of mfs, or you may say integer multiples of omega s. Omega s, 2 omega s, thrice omega s, etc. Same amplitude. Now if you insert this expression 1 by tau summation over m equal to minus infinity to plus infinity e to the power jm omega st into that earlier expression that we have considered, product of xt with a summation, what will happen? So this is the Fourier series expression. Omega s is the angular sampling frequency. Is it done, this part? Now move on to that expression. This was the expression where I wanted to insert that Fourier series expression in place of this summation. So that's what I have done. 1 by tau has been taken out. Oh, here there is a problem. Just 1 minute. All right, it has gone outside the screen. Can you see it? Is it visible? Is it?
Yes, sir.
Can it
Yes,
be clearly seen?
Yes, sir. Yes,
Yes.
sir. Yes, sir.
1 by tau has been taken out, and remember that xt multiplied by e to the power j m omega st. What is that? It will be x j omega minus j m omega s from the complex exponential multiplication property of Fourier transform. So there will be several innumerable such terms. Xt into e to the power j omega st, xt into e to the power j2 omega st, xt into e to the power j3 omega st, like that, and also for the negative side. So ultimate result will be 1 by tau times this summation. So that is in the frequency domain. You can write it also as 1 by tau xj omega convolution of that delta term. This particular step is not important. What is important is x at j omega can be represented by 1 by tau times summation of what are these things? Xj omega minus omega m omega s. What does it represent? It is same as xj omega. Its shape is nature is same as xj omega. Only thing is that it is centered at m omega s. So it's a version of xj omega that has been slided along the frequency axis by m omega s. Therefore, this summation will be infinite number of replications or repetitions of xj omega centered at integral multiples of the sampling frequency. All right. And those repetitions, each of those repetitions will be multiplied by 1 by tau. Now, all these infinite number of repetitions multiplied by 1 by tau will get added to yield x hat j omega. In the next step, for simplicity, I am assuming that xj omega is a positive real valued function of omega, just for the sake of simplicity, just for the sake of illustration, more precisely. If xj omega is a positive real valued function of omega, what does it imply? It implies that xt has only amplitude spectrum. I have written there is no phase spectrum, but that should have been written in this manner. The phase spectrum is 0 for all values of omega. We have written it, these steps.
Yes, sir.
No phase spectrum, I shouldn't have written. Please write the phase spectrum is 0 for all values of omega. Then instead of xj omega, I may write x omega. So this is x at omega. That is the expression, or you may also write, instead of 1 by tau, you may write fs, the sampling frequency. So what will happen if you sketch x at omega as a function of omega? Will it be a unique sketch or unique plot, or it will depend on certain condition?
Done. Done, sir.